Hi, everybody. Bob Chesebrough. We're going to be talking about Intel extension for Scikit-learn to accelerate machine learning frameworks. So let's start with just some of the learning objectives. So just at a high level, I want you when you come out of this, I want you to be able to describe the value of the AI analytics toolkit that wraps the Intel extension for Scikit-learn, understand a little bit about what the Intel extension for Scikit-learn does, how this patching mechanism works, what some of the underlying libraries. Not every algorithm in Scikit-learn has been optimized by us, but there's a good chunk of them that have. And so I want you to be able to identify those classification, regression, clustering, and so forth, these algorithms that have been accelerated, so you know from your Swiss Army knife in your pocket what's going to run very quickly, and then how to apply the patch with just a couple lines of code. And then we're going to see if we can squeeze in this topic of compute follows data. And this is how we could apply the Intel extension for Scikit-learn algorithms, those accelerations, to the Intel GPUs. And so with that, let's go ahead and get started. I'm going to go through these slides because fairly quickly, I have a feeling that many of you have seen this introduction several times. So I'm going to do it for those of you that haven't seen it. This is everything I'm going to talk about today is underpinned by one API. Now, one API is an industry initiative. It's not an Intel thing. It's an industry initiative, and it's promoted by the Kronos group, and the underlying technology is called Scikit. And so one of the things that you may have taken classes, you may have done some of these webinars or workshops from some of my colleagues explaining how to use Numba or how to use Scikit and the OpenMP and these things to accelerate some of your workloads at kind of this lower level focus. We're going to up level it to a little bit higher level in sort of a framework level that's built on top of all that. And so this industry initiative, we've got our reference implementations of that initiative. And we have several toolkits that use this technology, the one API under the hood. And so we have a rendering toolkit, we have the Internet of Things toolkit, the HPC toolkit, OpenVINO, the Intel distribution for OpenVINO toolkit, and so forth. Today's focus is more specifically on the Intel AI Analytics toolkit, and I'm going to decompose that a little bit for you. We're going to be just talking about one component within that called Intel extension for Scikit-learn. So if you've been following any of these series that we've done, Intel and Argonne and this Aurora, training, you've probably taken some courses, some of these lower level things. We're going to be focusing on this middleware frameworks up above. And I just want you to know that Intel does supply these optimizations that we cooked in this toolkit. We give those to the TensorFlow community, to the PyTorch community, to the NumPy, XGBoost, OpenVINO community, and so forth, to accelerate those things in their stock versions, okay? But then we also have the toolkit, because there's a difference in the cadence at which the release of the stock version happens versus the release of our toolkit. Our toolkit typically is refreshed much more quickly, a faster cadence. So there may be extra performance things you can do in the toolkit that aren't yet in the stock. So I wanted to call your attention to that. But here are the kinds of things that we do accelerate. So on the deep learning side, we have extensions for Intel optimization for TensorFlow, Intel optimization for PyTorch, Intel neural compressor. Now, again, these things would help on the deep learning side to accelerate either inference and in some cases also the training. But we also work very hard to promote those same optimizations in that cadence in the TensorFlow main lines and the PyTorch main lines and so forth. Then on the machine learning side, we have the Intel optimized XGBoost. And when you download right now and you just install in XGBoost, you get the Intel optimized version. But our toolkit may have some extra speed ups that haven't gone into their release cadence yet. And then for Intel extension for Scikit-learn, the methodology is somewhat different. We apply a patching mechanism. So I'm going to describe that for you. We also provide these optimizations under the hood through one API, and through the AI Analytics Toolkit. Effectively, we have accelerated versions of NumPy, SciPy, Pandas, Numba, and so forth. And some of these courses you may have seen or heard, or we'll be going through more of them later. So I just want to describe a little bit about what we're focusing on, this specific subcomponent of the AI Analytics Toolkit called Intel Extension for Scikit-learn. And just to acquire it. So it's the usual suspects. So you can either acquire the Intel extension for Scikit-learn by itself and pip install it, and you can go to this link with a white URL there. To get started with that, you can download it and do a pip install for just that subcomponent, or you can download the broader Intel AI Analytics Toolkit, and that includes the TensorFlows and the PyTorches and all those things. So that is the comprehensive library, and that's in blue down below. And so you can do a conda install. It's all the usual suspects: conda, pip, Docker containers, and so forth to acquire the library. Now, if you're going to be following along with us in the workshop on November 9th and then on December 14th, the December 9th one will be focusing on the CPU accelerations. The December 14th one will be focusing on how to use these Scikit-learn optimizations on the Intel GPUs. So if you're following along with us on those, you will either be using the JLSD server, or you'll be using the dev cloud, and I'm going to be teaching it from the perspective of the dev cloud. So you won't have to go through this installation process. If you want to do it though, this is where you would go. So the motivation here is to articulate how you achieve acceleration on Intel CPUs at both current and future Intel GPUs to be ready for these future innovations coming down the road from Intel. And how you can do that with just a few lines of code. And I'm going to articulate a couple of methodologies that you use to do this, and then I'll be showing you some of the code just in our little webinar where you're going to really understand this. So this is setting the context and the framework so that when you come and join us in these workshops, you're going to see how to apply these in sort of real world scenarios or real-ish scenarios. I can't make them totally application specific, but hopefully more than just the little toy examples. And so you'll see how to do these things. But this is the procedure for ignition. The thing that you do here is that you, on the CPU side, you just use a couple lines of code. It's an import and a function call to apply what we call a patch. And I'm going to articulate that for you going forward here. For the Intel GPU, there's an extra step that's a methodology called compute follows data, and I'll be describing that as well. So what's in it for a developer? Well, in a sense, it's time. It's buying back time. It's using your time more efficiently. Effectively what you see here in the background are some of the speed ups. This is posted on GitHub for some of the benchmarks that they've done on various systems and so forth. This is just one that I cherry picked, but this is the training side. So this is the fit functions for all your old friends from Scikit-learn, the dbscans, the kmeans, the k-nearest neighbors, the random forest, all these different guys. So the training accelerations are on those orders of magnitude, anywhere from 2 up to, could be 100 or so. And then for the inference side, that is to say the predictions and the transforms that you might do on PCA and so forth, then those speedups are this kind of outset version of the graph. And this shows that it does depend on the nature of your data. If you're using k-means, it depends on the size of your data, the complexity of your data, how many columns, how many clusters are in your data set for the accelerations you get. But generally, it's always a good value for you to use it. And so there's 23 commonly used ones. I'm going to be articulating roughly 20-ish, just very quickly. And then when you come in to do our lab, our workshop in November 9th, you'll get hands-on experience on how to do some of these things. And I think there's some cool surprises for you in that workshop if you join. I'm about to transition. So Yasi, are there any questions for me so far?
Nope.
Okay.
Oh, you can continue.
I'm going to keep flying. So here we go. Here's the gallery of optimizations. This is the what. Okay. I showed you the motivation why. Now I'm going to describe the what. So the whats are these guys. On the far left, you have the unsupervised learning routines, like the dbscans and the k-means, which you use to do clustering. Right? This is that idea of you have a bunch of dots and it's a Rorschach test. They're just dots on a 2 or 3 or n-dimensional space, and you are trying to figure out if some of them are located near each other. Do they form groups like clusters of grapes? Well, then you use these algorithms. Nearest neighbor and its relative, its progeny, the k nearest neighbor. Nearest neighbor is an unsupervised learning algorithm that's used. You just give it the feature data. You don't need to give it your wire label data, and we'll find nearest neighbors in a data set. Principal component analysis is a very heavy hitter. It's one that you use all the time in machine learning, and we have accelerated versions of that. TISNI is a dimensionality reduction thing, typically to compress large complicated data spaces down to something in 2 or 3 dimensions that you can visualize. We've accelerated those. Linear regression and its offspring. Linear regression, lasso regression, where you use a L1 regularizer, a ridge regression with the L2, ElastiNet, which is uses both L1 and L2 regularizers. These things are accelerated. Logistic regression, which oddly enough is actually a classification routine, is accelerated. A k-nearest neighbor, both the classifier and the regressor. The random forest classifier and the regressor, the support vector classifier and regressor. So these are support vector machine type applications. And then some of the routines that are more utilitarian in its nature. You know, the assert all finite. So you take NumPy array, you know, ND array, and you want to determine that everything in there is finite, there's no nans or whatever. Well, then we have an accelerated way to report that and get that done quickly. The ROC AUC score, that's the receiver operator characteristics, are under the curve score. This is something that's used to kind of score your metrics, and so we have an accelerated version of that. Train test split is one I use all the time, and we have an accelerated version of that. Pairwise distance is one that many people don't think about, but pairwise distance, I can show you some cool things that we do to analyze stock data and a stock portfolio with 500 stocks that you will see in our workshop if you come to our workshop, and how you can use pairwise distance to find those stocks that match a pattern. And so these are just some of the things that we talk about. Now on the GPU side, we have optimized fewer of these, but these are the candidates here that we've accelerated for the GPU. So it's just the subset of the ones I described before. And so any questions now, Yasi, on what I've covered so far?
Oh, I don't see any questions in the chat, but if the attendees have questions, you can unmute yourself now and ask.
Okay, I'm going to keep going. So again, this is kind of along the lines of the motivation. I want to invite you to this workshop we're going to do, because you will generate this curve. And so what this does is this compares the stock library for the Intel extension for Scikit-learn. In this case, it was for the I remember which one it was. It was the KNN algorithm. So this was KNN on a particular data set, the synthetic data set that we created. But this was just showing the patched version versus the unpatched. And this was something north of 50x speed up that we got on the Intel Dev Cloud. And so you will see this, and you'll be able to play with this. Similarly, you'll be able to create this graph. You will actually generate this graph and you can manipulate it. I created a little test harness that you can use in the workshop to be able to test whatever you want of the accelerated ones that we have, you know, whether it be support vector classifier, logistic regression, KNN, PCA, whatever, what have you. You can plug it into the test harness, and what the test harness allows you to do is to pair synthesized data that you control, the number of samples, the number of features, the number of columns, you know, how many of the columns are interdependent upon each other, how many inherent clusters are in that data. So you can generate your own data, pair it with the algorithm with whatever parameters that you wish, and you can see how that would, you can try it on. It's like going to the fitting room and you're trying this thing on. So you got a test harness to be able to do that if you come to the lab. And so you will generate these curves. And in this case, lower is better. So the blue bars show what happens as a result of patching. And again, the orange bars are the result of just using the stock version. And so what you do in the lab is you're actually going to feel in the muscles in your legs as you sit and do this, you're going to feel the essence of time, whether you want to use a patch version or whether you want to accelerate it. And so this is in multiple modalities. You will begin to learn visually and actually tactically, haptic sensors in your legs, this sense of time that you get back by using these these deals. So I'm going to go into patching. Go ahead and type in any questions if you wish. I'm going to keep going until I start to get some questions. So Yazi, slow me down if you wish. The meat is coming up. So I want to introduce this idea of patching. This is this sentinel, this listener that we set up, that we cause to listen for any future lines of code where we request the import of a Scikit-learn library. And then that patch will then say, they're asking for the KNN library, or they're asking for a PCA, or they're asking for whatever algorithms or multiples of those imports that you wish. And then it knows, okay, I'll give you the optimized version of that if you set up that patch. Now, there's a number of ways that you can apply the patch. There's a strategy that you can actually use. Patching is very easy. I could do it with an environment variable if I wished. And then any time on that system, if the environment is variable set, I could just automatically have patching applied. I like more control than that, so I tend not to use the environment variable. But I could do it on a single line of a command line. Just one single command line. I could take my Python code, and I'll show you this just here in a few slides, to issue a command to apply the patch to the entire Python file. Or I'll show you how to do it within a Jupyter notebook. So for a given cell, or for everything following that cell. And then there's also unpatching. And this combination of patching and unpatching with the various ways that you can patch, I'm going to show you today, will allow you to guarantee that you keep the best performance. You'll get the best performance, and if by some chance you happen to find that one of these patch functions in your particular case, for your particular data set, slowed down, you haven't lost anything, because you can just choose which one works fastest and you can apply it. And I'll show you how to do that. So this, from a high level perspective, this is just how you do this in the command line. If you have an application, a Python file, my application.py, you just say python-m Scikit-learn-ex and it's patched. If you're inside a Jupyter notebook, you say from Scikit-learn-ex, you import the patch, and then you patch it. You invoke that listener, that function call, patch Scikit-learn, okay? So that's how simple it is. And if you were to stop the webinar right now, you'd be miles ahead. But let's keep going, because there's some nuances that I can teach you about. And some of these nuances are the following. You can unpatch, and this looks very similar to the previous line, but just with the prefix un in front of it. And now we can unpatch. So you can patch a few cells and unpatch a few cells if you wish. Or you can surgically control it. You can say, I only want you to patch SVC, or I only want to apply the patch to this list of SVC and PCA, or I want you to unpatch a certain thing. Okay, so you have explicit control of the patching mechanism. And so getting the list of optimized functions, this is just a utility thing. Just I wanted to let you be aware of it, that you could actually get the names of all the functions that we have patched and that are supported. Now, so 2 lines of code is very easy. Why do I need a webinar for that? Well, it's very easy. I agree. Knowing where to put those patches can be important, and so how you do it. So the most important thing that you take away from this webinar is that when you apply a patch, that is to say, when you say that you've imported it and then you've issued the function patch Scikit-learn, you have to do this step before you do any of those other imports. If you did this import, say in this line of code way above, let's say I imported KNN, okay, K nearest neighbor, then it would not be patched, because that import happened before we knew to listen for it. So this is only going to patch those things that you import after you apply the patch. If you get that in your head, then you will have all kinds of success in accelerating whatever you want to accelerate. So this guides you where to apply the patch. And if you're willing to apply the patch to everything, just put it at the very top cell in your Jupyter notebook and you're good to go. But I just wanted to let you know how that works. Now, what does that mean about how to use the stuff now? I've patched train test split. How do I call it? Well, I call it just the way I've ever called it before. I didn't change any of the rest of the code at all. It's just the same use. The only thing that I did is I applied these 2 lines of code, and I applied them before I imported. And there you go. And that's how you do it. So this is just an example of some of the things you're going to see in the lab. This is one of the snippets from that test harness I was describing, where you have the support vector classifier, the linear kernel. And so this is the one we're going to import, and we're going to bind to it data as defined in the following way: number of samples, however many you want, and number of features, this is how many columns, and the number of classes, and how many of these are informative. So that, in other words, some things are completely random and some things have linear dependencies among them. And so you can control all this stuff. And then it's really applying the patch right here. And this is just showing it how it's going to look in the lab when you do it. You apply the patch, you do the import, and then you use it. And then you get these results. We plot the times right here. And so these are the kind of speed ups that you would get typically. So I'm going to switch gears now. So are there any questions? Just we've been talking more about the CPU side or patching in general. You do use the patching also with GPU. Before I go into the GPU discussion, are there any questions so far on patching?
Yes, I have a question. How do you go about patching and unpatching so that you can mix up different functions?
And we'll see this in the lab. If you get a chance to come on November 9th, you'll see this. There's a whole exercise, several exercises on how to do this. It's really quite simple. If you want to patch everything, you would just apply that patch at the top cell and everything, and it will stay listening until you explicitly say unpatch, and then it will stop listening. And so anything that you import between the patch and the unpatch will then be patched. And so, and then anything, and you can surgically control it as well. So that you could say, like I said, you could just import the patch just for a specific function if you wish, or whatever. So you have infinite control, but the idea is that you can turn the patching on and off. It's almost akin to, analogous to a house. And when we apply the patch globally, it's like turning on the breaker switch on for all the electric in your entire house, okay? Well, that's fine, your whole house is electrified. But then when you go into each individual room, you have a specific switch that turns on or off the lights in the room. You can do that as well. And so if you wanted to globally unpatch, let's say, you can effectively control down to the LED level, practically, what lights are turned on or off in your house at any given time. And the way you do it is just by applying that patch. And any import that you do after you do the patch will have the patch applied if we've accelerated it. So of that list that I showed you, that 32 items, I described roughly 20 of them to you. And then when you say unpatch, it will then revert back to using the stock version. Does that answer the question?
Yes, thank you.
Yep. So I'm going to keep moving on. We're going to talk.
I have one more question.
Yes, go ahead, Alex. Yes.
So this patching is not permanent, is it?
No, it depends on what you mean by permanent. You apply this patch in your code, and so from the dynamic extent of the code, as the thread goes through that line of code and turns on the patch, it will apply it. And then when you go when then you unpatch it, it does that. So it depends on what you mean by permanent. But
so this patch applies only within the run, not the environment or the actual the library itself. Okay.
That's right. That is exactly right. Now there is a environment variable that you can turn on to just by default patch anytime you use Scikit-learn. And I didn't cover that here. It's just my personal preference. I just feel like I lose too much control. I'm a control freak. So I don't like to do that. I want to be explicit. But if you want to just do that blanketly, you can do that with an environment variable. And so that would be purely automatic at that point. And so now we're going to talk a little bit about how this compute follows data thing works. And I just want to set the caveat. And when we do these labs, I'm going to be doing these labs in the future. We're not doing the lab today. We're going to be doing it for the GPUs. We're going to be doing this on December 14th. But my goal here is to tell you how to target the GPU with Scikit-learn extensions, the one that we've optimized. My intention is to not show the ultimate GPU performance, because on the dev cloud in particular, the GPUs we have are not the real high performance parts. So I just want to set that caveat that I'm showing you how to do this, and this how-to will apply to any of these performant GPUs that come down the stream, or the ones that you have access to already on your GLSE server. So the compute follows data is achieved through a support library, and the support library is called dbcontrol. And it works in tandem with what I've taught you already about patching. So you're going to enable the Scikit-learn methods. So the ones that we've optimized, then you can have computed on a GPU, the Intel GPU. And then what happens is any of those methods follow the data. You're going to cast your data, say your X variable, you're going to cast that to a DP control tensor where you specify what the device is, what the accelerator is, GPU 0, GPU colon 0, whatever. And then that data gets bound to that device through that variable. And then any computation that you do on that variable is done on that device. And so that's called compute follows data. And so just some background about the library. This is the import of the DP control library. You can import it. You can get a list of all the devices and what their names are and what their particulars are, what their driver versions, the names, and so forth. But this is how you can set up some flags so you can say, yes, I have a GPU available. In systems where you don't know whether you have a GPU available or not, like sometimes you have a node and you want the code to be able to run on CPU nodes, or CPU nodes also have GPUs on them, then code like this can be very helpful to say, hey, I happen to be on a node that has a GPU available or not. And so this is just boilerplate that I use to kind of make it more general. So the concept is very easy, but I'm just trying to set up, I'm getting the devices from a queue, and then I'm saying, look, if any of those devices in that queue is a GPU, then go ahead and say that, hey, we have a GPU available, and so forth. So it's very, very simple-minded. But what you have to do is you do have to apply the patch. You apply the patch, then you do the import as before, okay? Now what we can do is that we will cast our data. So this is those features from our tabular data. It's in a variable called X. And so we're going to convert that variable X to a DP controlled tensor using the as array. You can actually use to or from NumPy function as well, but I think as array is more general. So you could say DP control tensor as array, give it the variable that's on your CPU, X, that's my X data. And then I give it the device, device is equal to GPU. Or I could say device is equal to GPU colon 0 or GPU colon 1, what have you, okay? And then I call the kmeans function. Now this kmeans fit function, just so you know, if I just put the uppercase X in here, right, in place of the X device, I don't know if you can see my cursor, but over here on the right side, let me go back. I could put the uppercase X where it says X device there, and then that would be computing that since X resides on the CPU, I would be doing the fit function of kmeans on the CPU. But since I've converted this tensor is a DP controlled tensor and it happens to know where it lives on the GPU, then I'm going to use the variable, the handle that's name is called X device. So if I call this function on X device, then that computation is done on the GPU. And then that result is returned back to me. And there's some caveats I'm going to talk about later about what we do with those return values. So, so what we're going to do is we're going to cast. Now, typically for most methods in Scikit-learn, you have X data and you have Y data. Okay, the labels and then you have the features, features and labels. And so what we do is we cast each of those. We cast the X data, we cast the Y data. And so now I have GPU-ish versions of that same data, okay, but they reside on the GPU with the X trained device and the Y trained device. And now when I say random forest classifier and I say fit, I just give it the data from the GPU, so X trained device and Y trained device. And then I get a return. So CLF is just the return from that fit function. So it's all that information about the fit function and the values. But then if I want to do a predict on that data, then what I do is I would call the predict function, and I'm going to call it on, let's say, the test device data. And I didn't explicitly show you here, but it's also tensor data, DB control tensor data. So I'm going to do a prediction. I get the prediction under predicted GPU. Predicted GPU is itself a DB control tensor, which is not useful for the rest of Python, like if you tried to print it or whatever. So I need to cast it back to be a NumPy, ND array, which is what typically is returned from the stock version of the same random forest fit. So I'm going to cast it from the DP control tensor back to the ND array version, which is now called predicted GPU. And so with that, you have the conceptual knowledge to be able to do NumPy or do Scikit-learn acceleration on Intel CPUs or GPUs with just these few lines of code. And so I just wanted to describe a little bit more about this. When do you cast? You know, what types of data do you cast? Well, typically on the fit function, typically in Scikit-learn, I haven't found a counterexample to this. The fit function almost always returns a self object. And if it returns a self object, you don't need to cast it. You do not cast it. So fit, you don't cast. Okay. Now, fit predict typically in the stock version of Scikit-learn returns an ND array. And so that means that if it's on the GPU, it won't return the ND array, it will return the DB control tensor instead. So that means we do have to cast it back to a NumPy array. Same thing with predict, same thing with fit transform, same thing with transform. So if you're going to do it, all you have to do is make sure that you have this extra line of code that takes your result from your prediction and you cast it back to an ND array as follows. So it's not a hard step, it's just something you have to remember conceptually, and that's why we put these slides together. So that is pretty much the discussion, and I went through this fairly quickly. I do want to set you guys up, so if you want to play with this, I'm going to share with you the GitHub links, but we're going to be doing this. I'm going to be leading these on the Intel Dev Cloud, so I would really encourage you guys between now and November 9 to go ahead and enroll in the Dev Cloud. And let's get started so that you're ready to go ahead and do this, because you're going to be seeing how to use, for example, like that stock example, I think with using the pairwise distance is something you may not have seen much of any place else. And we've got an image clustering example that you can play with. We have a galactic collision of two galaxies that I simulated some data, synthesized two galaxies in a cosmic galactic. We're going to do some classifications on those with various algorithms. So you'll get to exercise these principles in more real-ish world scenarios where we're going to say, well, I'm not just optimizing one function. I have to call several functions in succession. How do I do that, right? So you'll learn by doing, you know, a number of these things. So go ahead and enroll for this if you would. And then here's the repo. You can get started right now. I keep making changes to this, but you can just do this git clone and you can start playing with these algorithms right now. For November 9th, we're going to be playing with units 1 through, I believe it's 4. And then for December 15th or December 14th, I'm sorry, that's the GPU exercise. We're going to be focusing on modules 5, 6, and 7. And then if you're patient with us later on this year or in 2023, we are going to be covering how you accelerate with NumPy. And that NumPy one is going to be pretty juicy. You're going to get some really good speed up. So we're hitting multiple levels of programming. Scikit-learn is a little bit higher level of abstraction. NumPy is a little bit lower. But and then we've got some XGBoost stuff coming out. We've got a number of things that we'll be able to show you. So stay tuned. But if you want to get started, this is where you would get started with the code. And I just wanted to really encourage you to continue the series, because there's going to be some cool things that you get to experiment with that maybe you haven't played with before, and some new ways of thinking about Scikit-learn in addition to just the optimization step. So please join us. This is the link to it right here. And I'm going to set it up for any kind of Q&A right now. I'm going to just throw this up here to give us any feedback. If you'd go ahead and just click on this QR code